Hi there, welcome. It's Chem Coach Powers with another exciting day of chemistry for you. Today we're going to be learning about ionic compounds. What is an ionic compound? What makes it ionic? And as we go through in some future lectures, we'll talk about covalent compounds and things like that. Should be a short lecture for you today, so yahoo! Here we go. Start with our objective here, okay? Our objectives are to describe an ionic bond as electron transfer or the attraction between a positive and negative ion. And then what is meant, understand what is meant by a crystal lattice and a formula unit. What do we mean by those things? So your success criteria, you get out of here. You should be able to describe the structure of ionic compounds in terms of cations, anions, and a crystal lattice. Tell me what that means. And we'll talk about lattice energy as well. And explain how a formula unit can be identified from crystal lattice. What does that mean? Well, you'll see. And what is that in terms of what's different from a crystal lattice that's an ionic formula unit versus a molecular compound. Okay, so let's talk about what we know already. So just a little bit of a reminder, we've learned about ionic bonding already, but remember that atoms are either gaining or losing electrons, okay? So if they are going to gain electrons, they're going to become anions, and if they're going to lose electrons, they're going to become cations, okay? So this is, remember, this is gain electrons, and it's going to be a negative charge. Okay, it's going to be negative overall. This is going to be lose electrons, and this is going to be a positive charge, right? So there's a little bit of review there. Remember that these negative and positives are going to be attracted to each other. So if I have a positive sodium and a negative chlorine, they are oppositely charged, so they're going to come next to each other. Okay, that place where they're coming next to each other, that is the ionic compound, and that's a strong attraction. And these are strong bonds. These are strong materials, strong solids. Okay, if we look at a sodium chloride crystal, we can see that we've got a whole bunch of sodium surrounded by a whole bunch of chlorines. Okay, same thing that we have as a model here. This, all the little green ones are chlorines and the silver ones are sodiums, let's say. And you've got every little sodium surrounded by 6 chlorines and every chlorine surrounded by 6 sodiums. It's kind of cool to focus on just one thing and see how they're all surrounded by that. And that's in 3-dimensional space. Here I'd be like, hey, how many chlorines are surrounding every sodium? You'd be like, yeah, 4. Well, yeah, but you got to remember to think in 3 dimensions in chemistry. And so if I look at this sodium right here, it's surrounded by 1, 2, 3, 4, 5, 6 chlorine. So it's actually surrounded by 6, right? Each of these is surrounded by 6 others. So it's kind of interesting to think about that. Now, remember that ionic bonds, quick and dirty way, metal and a non-metal combination. But remember that the true way that we want to look at this, that is a little bit less arbitrary, is finding an electronegativity difference less than, you remember it? 1.7 is going to be the number that you're looking for. So less than 1.7 is covalent, and greater than 1.7 is ionic. So I said less than, but you know what I meant. Greater than 1.7 in order for it to be ionic. Okay, so just one more time, let's go through and use the model of the atom that Bohr came up with to kind of show us how these ionic compounds form. Okay, we're just going to create something that has 1 valence electron, that's sodium, right? And then for chlorine, we are going to create something that has 7 valence electrons. Okay, I think I did it. Remember that this sodium wants to have 8, and so it wants to get rid of its 1 electron so that chlorine can take it, and chlorine, and it doesn't care what chlorine does, but chlorine wants to take it because it wants to have 8 in its outermost energy level. And so once sodium gives up its 1 electron, remember it had 11 protons and it had 11 electrons. Chlorine had 17 protons and 17 electrons. Now chlorine got 1 extra electron, that means it's at 18. And that means it has a 1 negative charge now. And sodium gave away its 1 electron, so that means it has 10 electrons. And that means it's at 1 positive right now, right? So this transferring of electrons is what's taking place when you have ionic bonding, okay? A quick transfer of electrons. Now, this is different than it is for covalent compounds. And covalent compounds, we'll talk about sharing. Ionic compounds are transferring the electrons. Okay, so we've got a couple questions that I want you to think about. Now, if we were in a classroom setting, you'd turn and talk to somebody. But I want you to contemplate in your own mind and maybe in your notes then. What's the difference between an atom and an ion? Try to write that down in your notes, please. How can an atom become an ion? Just put it out on your notes. And why do atoms become ions? Okay, so let's just talk about those as if I'm your turn and talk. You've written it on your notes. Atom is not charged. Okay, an atom has the same number of the protons as it does electrons. Ions will be unbalanced, and it's going to have a charge. How can an atom become an ion? By losing or gaining electrons. Why do atoms become ions? In order to get to a more stable energy state. Remember, they want to go to a lower potential energy state and to try to give away some of those electrons or gain some of the electrons in order to get to that more stable energy state. Remember, a cation is a positively charged ion. Okay, positively charged ion. Metals have less than 4 valence electrons, so they are going to lose. So anything at the middle, so in groups 13 all the way down, right? All of those guys, 13 and down, are going to lose. I'm going to just say groups, because there are some metals that are in those other groups, right? Groups 13 and below are going to have less than 4 valence electrons, so they're going to lose, okay? And so again, remember that cation is a positive ion, positively charged ion. Aluminum, for instance, has 3 valence electrons, so it's going to lose 3 and become a 3 positive charge. The anion is that negative ion. Again, just a little bit of review here. Doesn't hurt to know it again and know it and know it and know it. And this is going to be groups 14 and above, okay? Or 14 is kind of that middle line where it could go either way a lot of times. And so we're going to go ahead and say groups 15 and 16 and 17, okay? So we're going to just go groups 15, 16, and 17, sometimes 14. Okay, and then this one could be, you honestly could be like sometimes 14 here, right? Since some of these could be losing electrons as well. These guys are going to gain electrons. So if you're in group 15, you're going to gain 3. Group 16 is gaining 2. Group 17 is gaining 1. And remember, nitrogen has 5 valence electrons. It wants to get 3 more so that it can have, remember, it's trying to get to that 8 number. It's trying to get to the octet. They want to be like the noble gases. Notice I didn't include group 18 here. Group 18 doesn't form the ions. They're already stable. They don't want to form an ion. All right, so our ionic compounds, clicking all over the place here. All right, so let's look at ionic compounds. We have these positive and negative charges, right, that are coming together, and they're going to have an equal number in that whole structure. And these are going to exist as crystalline solids. Now, I have an example of a crystalline solid here. All right, this is a selenite crystal, which is calcium sulfate, I believe. And so this is an example of a crystal. It's a 3D network of the cations and anions all interconnected, right? They're not independent. You don't have molecules. And like the difference, you know, that calcium sulfate is going to be kind of like this, right? Where it's got a definite structure. If I were to looking at water as a difference, okay, so here's an ionic compound, here's a molecular compound. This molecular compound can be interconnected as well, but it's connected with these hydrogen bonds, represented by a little piece of white plastic here, versus the green plastic. The green plastic is the representation of a covalent bond. And so the covalent bonds are holding the oxygen and the hydrogens together. This is water. And so a molecule can be independent like this. It can be a single independent unit. And then it can also come in contact and be together and be using those hydrogen bonds to form a crystal. But these guys don't act like that. These guys, if they come apart, they don't like stay as a group of Na and Cl. Okay, they don't stay together. Oh, here's an Na and a Cl. They are breaking apart into individual components. Unlike the molecule, which will stay cohesive as this unit, the sodium and chlorine don't stay cohesive as a unit. They break apart into sodium and chlorine. That's going to happen, for instance, when they're in water. All right, so they don't have these independent units of sodium chloride. They don't form molecules. They stay separated. Now, although they are forming crystals, right? They form crystals like we saw that calcium sulfate, water, ice, sugar is a crystal, right? So molecular compounds can form crystals as well, but they don't form crystals in the same way because they don't use ionic bonds, so stronger bonds. They use covalent bonds, which are weaker bonds than the ionic bonds. Ooh, I just broke apart my little molecule here. It's not a molecule. My goodness, it's called a crystal lattice. For shame, powers, for shame. All right, here we go. Sorry. All right, so let's look at this crystal lattice. What is a crystal lattice? Tightly packed structure of cations and anions together. And again, remember, you can have crystals that are molecular compounds, but in this case, when we're talking about ionic compounds, they're cations and anions put together. And lattice energy is a specific term that talks about the energy released when 1 mole of ionic substances forms gaseous ions. Okay, actually, I don't know if they have a something called a lattice energy for molecular crystals. I'm guessing they might, but it's not something that we typically refer to in chemistry. We talk about the ionic substances having a lattice energy. How much energy? So if I had these things together, or had these things apart, okay, 1 mole of ionic substances forms from gaseous ions. Okay, so if I had them apart from each other, I had all this chlorine, all these little green ones as a gas, and then I had all these little silver ones, sodium as a gas. It had to be really hot, right? Sodium is going to be really hot as metal. And I have these things in a gaseous container, and all of a sudden I electrocute them. What happens is as I apply that electricity, these two separate gases actually come together and they form the salt. And these things, when they get electrocuted, will actually form little crystals, okay? And the amount of energy that they give off when that happens, because they're getting to a lower potential energy state, right? The amount of energy that they give off when that happens is called the lattice energy, okay? All right, so we also have an interesting name. It's called the formula unit. When we talk about a molecule, okay, we talk about having a molecular compound, but we really want to refer to the ionic compounds with formula units. Okay, the reason we do this, the reason we use this term is because we want to talk about the whole number ratio of ions that are in that compound. So if I look at this and I count everything up, one of the objectives was, hey, if I looked at a crystal lattice, could you tell me the structure? Well, the idea here is that you're trying to figure out how many sodiums you have, how many chlorines do you have, okay, and you're at a 1-to-1 ratio, then you can say, oh, my formula unit, my unit of my ratio of sodiums to chlorines is a 1-to-1, and so I just say, oh, NaCl. Okay, that looks horrible the way that I drew that. That's because I was drawing it down by my navel. All right, I was trying to draw an N. NaCl, right? So if I've got sodium chloride, it's 1 sodium for every 1 chlorine is kind of the idea here. And that's kind of what you're getting, you know, if you count these things up. That's the idea. Can I look at a crystal lattice and figure out the ratio and figure out that it's a 1-to-1 ratio? And that's basically what you could do here. Oh, okay, we've got, you know, silver, green, silver, green, silver, green, silver, green. Like it's a 1-to-1 ratio, right? So I can determine the formula unit. It's a 1-to-1 ratio if I look at that actual crystal, right? Because the formula unit is the unit that describes how many of these there are for how many of the other ones. And that's not the case. Like for sugar, if I were doing sugar, and let's say I was doing glucose, C6H12O6, that is independent, okay? Just like H2O is independent. They exist on their own, and I would not use the word formula unit to describe those, okay? I would use that, I would basically say that they are compounds, okay? Those are molecular compounds. And in an ionic compound, I would say, hey, this is a formula unit of sodium chloride, okay? So it's just a special term that we apply to ionic compounds to describe the ratio that they have of those different substances. And the molecular compounds exist as separate units, and so they don't have that same type of thing where it's just a 1-to-1 ratio. You can actually say, hey, this is C6H12O6, and that's exactly what it is. But when you say NaCl, it's like Na 100,000, Cl 100,000. You don't know how many of these little guys there are, okay? And so it's a different way to describe things. All right, so we don't talk about a molecule of an ionic compound. We talk about a formula unit of an ionic compound. So use that term, formula unit, okay? All right, so ionic compounds, remember that they're doing this to minimize their potential energy, right, to get that lowest potential energy state. They form crystal lattices, and they have this balance of attractive and repulsive forces, right? The negative and positives are attracted, but the negatives are repulsed from the negatives, and the positives are repulsed from positives. Once they get to this balance of the negative and positive attractions and repulsions, then they finally get to what we call our crystal lattice. And that particular set of attractions and repulsions is going to give them different shapes. So you end up with various different shapes of different ions depending upon those repulsions. This is not the same thing, but because this is actually a diamond, which is a molecular compound, but it would be kind of like this. Oh, I've got two different shapes because of my different types of attraction repulsions. Oh, I have a different type of shape. This is actually graphite again. Oh, different shapes, right? That's the idea here. It's not, although those are not great examples, that's the idea that you have different shapes based upon the different attractions and repulsions and different distances between the ions and how their electrons are arranged, things like that. Okay, so the next thing we want to show you, for instance, is those different shapes. Here I've got sodium chloride and calcium fluoride. Here I've got, if I was trying to figure out the actual formula unit here, I would see, oh wait, look, there's a couple calciums, a couple fluorines for every calcium. I've got these 2 yellows for every 1 purple, 2 yellows for every 1 purple. And I'd be like, oh, my formula for that is CaF2 because I've got 2 fluorines for every calcium. Over here, if I count them up, I've just got, 1 for every 1. And so they have different shapes. Notice how they have different cubic shapes, and that's because of that arrangement that they have there. All right, so again, just comparing the ionic and covalent bonding, we've got our ionic bonding where you're transferring the electrons, right? And you end up with a crystal lattice. And then we've got your covalent bonding where they share electrons between the two, and so they have these distinct units that they exist in. And again, just a little bit of a reminder that covalent compounds can form these crystals too, but they don't have as strong of an attraction because they use the hydrogen bonding between them instead of covalent bonding. And that's the example here that I have of water, right, with ice, that our ice is got these white bonds in between it instead of the green bonds, and so they're weaker bonds. Okay, we're getting there. We are almost done. Let's look at some of our characteristics of ionic compounds. Again, remember, it's a metal with a nonmetal, or greater than electronegativity of 1.7. Valence electrons are transferred. The structure, it's a network of ions instead of a distinct unit, right? Melting point, really high, okay? The state is going to be a solid. And then the conductivity, it's good. Now, it's important to remember that it's good when it's either a liquid or when it's dissolved in water, because you have to free up these little ions to actually be free to move around. This, as a solid, is not a good conductor of electricity. But if you can dissolve this and pull these little guys off into water where they're free-flowing, then it is a good conductor of electricity. If you can melt it where they're free-flowing around each other, it's a good conductor of electricity. We also want to talk a little bit about polyatomic ions. I want to make sure you understand that ions can be polyatomic as well, that you can have some examples where you have multiple covalently bonded things together, but they have an overall charge. So it's kind of like a covalent compound that has a charge, and so we call it a polyatomic ion. It's an ion because it has that charge. But let's look, for instance, at nitrogen surrounded by 4 hydrogens. We've done those Lewis structures now. We do those Lewis structures and we get something that looks like that. Now, this actually isn't correct because, I mean, it's kind of correct, but we have to have those brackets around it, right? Because remember, nitrogen has 5 valence electrons. Each hydrogen has 1. That means there's a total of 9 valence electrons, and I'm only showing 8, which means I have to show that that has a positive charge. So this is a covalently bonded structure, right? These atoms are being, those electrons are being shared, but the overall thing has a positive charge, because in order for it to be like this, it had to lose an electron. Nitrate would be similar, right? So if I did nitrate, let me do it up here. I've got nitrogen, I've got 3 oxygens. Remember, nitrogen has 5 valence electrons. Each of the oxygens has 6. That's 18 plus 5 is 23. If I do my bonds, 1, 2, 3, that's 6, right? So if I say, oh, 23 electrons, I've just used 6. Now I've got to do another 17. Okay, let me do that. 2, 4, 6, 8, 10, 12, 14, 16, 17? What was all? Huh? Okay, and so things are not turning out too well if I try to do that. So I've got to say, oh wait, remember there was that 1 extra electron that we added. Oh, that's right. I'm actually allowed to do 18 electrons. Okay, that sounds better. But I'm not quite happy. Nitrogen's still not happy, right? And so I have to do a little bit of sharing, take from the happy and share. Remember, this is one of those that has a resonance structure. And so now everybody's happy. Remember, I have to put that in brackets with that -1 charge on it, right? And so now I've got something that was covalently bonded where they're sharing electrons, but the whole thing has a charge. And when that's the case, it's called a polyatomic ion. Everything's covalently bonded inside, but the whole thing had to have a charge because it needed 1 extra electron in order to satisfy that. And where did it get that extra electron? Well, guess what? It probably pulled it from something like sodium. And I made like sodium nitrate or aluminum. I made aluminum nitrate. Or some other sort of cation. It would have gotten an extra electron from one of those metals that wanted to get rid of an extra electron. And that's how they form. Okay, so let's see if we learn what we're supposed to learn. Describe ionic bond as electron transfer, yeah? Between positive and negative ions. Goes from the atom that had the extra one and gives it to the one that didn't have enough, and okay, or wanted another one, had enough but didn't have enough. And so that's a positive ion then that's left over and a negative ion that's left over. What is meant by crystal lattice and by formula unit? Crystal lattice is that structure of interconnected network of ionic compound or ionic components, right? The ions. And a formula unit is the ratio I have within that structure, right? And can I take that next step? Can I then explain how the formula unit is identified from the crystal lattice? Yeah. I can say, oh, well, I got to figure out what the ratio is of all of these, and then I can come up with my formula unit. And why is it different from a molecule? Because a molecule is a distinct unit, a distinct separate piece that exists by itself, and this doesn't exist like that. Each of these components don't exist in a separate little component like that, right? All right, and then, yeah, we already did that one. Describe the structure of ionic compounds in terms of cations, anions, and the crystal lattice. Ionic compounds are made up of cations and anions, and they form a crystal lattice structure, and you get something really cool like selenite, calcium sulfate, I think. Anyway, hope you had fun learning about ionic compounds today, and now you know a little bit more, and I hope you continue to learn, and I hope you continue to enjoy learning chemistry, because chemistry rocks. Thank you for listening. Have an awesome day. Be kind to one another, please. God bless you.